Hello, so in this video I'm going to go over the 2022 Higher Chemistry Paper 1 questions. So to start off with, the element contains covalent bonding and London dispersion forces. So if it's got both of those things, then it means it must be covalent molecular in structure, which means it must be out of these options sulfur. Boron's a covalent network, neon's monoatomic, and sodium is a metallic lattice. So the graph below shows the relative quantities of energy equivalent to successive ionization energies for an element. The most stable ion formed from an atom of this element has a charge of. So you'll find the most stable ion is the one just before you get the big jump in ionization energy, because when we get that big jump, that's when we start removing an electron from a electron shell closer to the nucleus, so it's less shielded, and an electron from a full and complete shell. So that means the 2+ ion will be the most stable, because you can remove 2 moles of electrons before you get the big jump. For question 3, HCl has a higher boiling point than H2 because, so HCl, hydrogen and chlorine have different electronegativities, which means it will be a permanent dipole. It will have a permanent dipole in the molecule, so it can form PD interactions. Hydrogen, H2, it's a non-polar molecule, so it'll only have LDFs. So in that case, C is the applicable answer, because we've worked out that the van der Waals forces in hydrogen chloride, which are PD to PD interactions, are stronger than the LDF van der Waals forces in hydrogen. Question 4. Which line in the table would best describe elements that act as reducing agents? So reducing agents are themselves oxidized. It's always the opposite. And if you remember from Nat 5 even, oil rig oxidation is loss of electrons. So that helps us narrow down the answers first of all. We know it's going to lose electrons because it's been oxidized. Now, when it comes to electronegativity is the measure of an atom's attraction for bonding electrons. So if we're trying to remove electrons, we want its attraction to be low, which means that we want a low electronegativity. So it would be B. Question 5. The correct redox equation for the reaction of iron 2 ions with acidified dichromate ions is, so you'd want to look up the electrochemical series for this and find the iron electron half equations for those two things. So I've got the electrochemical series here. Here's the reaction for dichromate, and we're reacting it with iron 2. Now, because dichromate's a reduction reaction going from left to right, we need iron 2 to be going from right to left the opposite way. So if we look up this side, here's iron 2 here, so it's actually this equation we want. You do have an equation with iron 2 here, but it's going in the wrong direction. So because we're going from dichromate to chromate and we're going left to right with this one, we need the other reaction to be going in the opposite direction. So we need the iron 2 to be on the right hand side of the electrochemical series. So I've got the two equations that we've pulled out of the electrochemical series written here, and in order to get the overall redox equation, we need to get the electrons to balance. So we need to times this one by 6, which means we've got 6, 6, 6. That means the electrons can then cancel, and then everything gets written together. So the answer we're looking for looks like it's going to be D. So again, just watch out that you've got the correct irons. So not iron solid, iron Fe3+ aqueous. For these questions, with the ion ratios, you need to write the molecular formulas. So magnesium bromide, symbols are Mg and Br. Magnesium's valency is 2, bromine's valency is 1. So we swap them over, which means we've got 1 mole of magnesium ions and 2 moles of bromide ions. So the formula would be MgBr2. For then magnesium sulfate, MgSO4. Sulfate's charge is 2-, which means its valency is 2. Magnesium's valency is also 2. Swapping them over gives you 2 and 2, and then that simplifies to 1 and 1. So we'd have 1 magnesium, 1 sulfate. So now we use the ion ratios. So 1:2 ratio for the magnesium bromide, 1:1 for magnesium sulfate. Then the question tells us we've got 3 moles of magnesium ions. So because magnesium is in both, I'm just going to write this here for now. 3 moles of Mg. And then it's got 4 moles of bromide ions, so we can put that underneath the bromide. So now we can start using the ratios to work out the missing numbers. So if it's a 2:1 ratio in the magnesium bromide, we have 4 moles of bromine, then we must have 2 moles of magnesium here. Because there's 3 moles of magnesium altogether, we've used 2 moles here, which means there's 1 mole left for this substance. And then because it's a 1:1 ratio between the magnesium and the sulfate, that means we must also have 1 mole of sulfate ions. So A. Naming the ester. So when you're naming an ester, it's always a good idea to find the ester link and put a squiggly line through the middle of it where each side keeps an oxygen. The side with the single bonded oxygen is the alcohol, and that comes in the first prefix. And then the other side is the carboxylic acid, which makes up the second prefix. So if we count the carbons, we've got 1, 2, 3 carbons in the alcohol, so that'll be prop. And there's 1, 2, 3, 4, 5 carbons in the carboxylic acid, so that'll be a pent. So altogether we would have propyl pentanoate, so D. So for question 8, we're looking for the one that's not an isomer. So in this molecule, the isomers would need to contain an oxygen, and they would also need to have a carbon-to-carbon double bond, or a double bond. It could be carbon to oxygen double bond. And it needs to have 1, 2, 3, 4, 5, 6, 7, 8 carbons. So we can start narrowing down by the number of carbons. So oct is 8, so that's a potential. Eth is 2, hex is 6, so overall that's 8, so again, potential. Eth is 2, hex is 6, so again, 8. And methyl hept is also 8, so that's not going to help us in this case. So if we start looking then about to see if there's any that don't have a double bond in them. So octanone is a ketone which has a carbonyl group, so that involves a double bond. Hexanal is an aldehyde which also has a carbonyl group, so again it's got an oxygen and a double bond. Then hexan-1-ol, so that's an alcohol, so that's just going to have a OH group, so it'll got an oxygen but it's going to have too many hydrogens, so that's probably the one that's not the isomer. Then if we just check the last one, so heptan-3-one, that's a ketone as well, so it's going to have the carbonyl group in it, which means it will have an oxygen and double bond, so that is probably an isomer too. The line in the table that shows the 2 functional groups present in this compound, so we've got this one here which is a carboxyl, and then we've got this one here which is an amine because it's only got nitrogen in it, so that would be A. Which line in the table correctly describes the reaction of prenol with bromine solution and hot copper 2 oxide? So bromine solution tests for unsaturation, so it would react if it had double carbon-to-carbon bond. Hot copper 2 oxide is an oxidizing agent, so it would oxidize if it was a primary or secondary alcohol or an aldehyde. So if we look at the bromine first, it's got a double carbon-to-carbon bond, so that means it would decolorize bromine solution, so that rules out A and B. And then for the oxidation, here we've got the hydroxyl group. It's on a carbon that's bonded to one other carbon, so that would be a primary, which means you can oxidize it. So it would react with the hot copper oxide and you would get the brown solid forming. So for this question, the higher the iodine number, the more unsaturated the substance is because it will react with more iodine. So olive oil, can't write and speak at the same time, is more unsaturated or less saturated. Sometimes it helps to write this stuff down because it can get a bit confusing when you're looking at all the possible answers. So if we look down the answers then, palm oil is more saturated, so that is true because the olive oil is less saturated. But if it's more saturated, it would have a higher melting point. So that one's not true. Palm oil is more saturated and has a higher melting point than olive oil. So that is the true statement. But if we just go through the other ones, so palm oil is less saturated. Well, we know that's not true because we've identified that olive oil is. And then again, the same for the D. So then, which line in the table describes the step in the cleansing action of a soapless detergent? So the head is hydrophilic, it's ionic, so it will dissolve in water. And the tail is hydrophobic, so it will dissolve in oil, so that would be B. A secondary alcohol, you can identify these by their, so basically if it's a 1-ol, that's a primary. If it's any number bigger than 1 for where the hydroxyl group is, that could be a secondary or tertiary. And tertiary would be where the branch is on the same number as the hydroxyl group. So B would be a tertiary. A is a primary because it's a 1-ol. C is a primary because it's also a 1-ol. And so that leaves D as the secondary, as the 2-ol, with no branch on the same carbon. Compounds below are examples of flavour molecules found in some plants. Which line in the table shows the solubilities of these compounds in water and oil? So I always have a scan of the molecules for hydroxyl groups. If they have hydroxyl groups, they will be soluble in water. So vanilla and ginger are the water soluble ones. The other two are oil soluble. Cucumber flavour might confuse some people because it does have a carbonyl, which gives it a permanent dipole to permanent dipole interaction that could form, but there's too much hydrocarbon for it to be very soluble in water. So just usually always look for hydroxyl groups and they'll be the ones that are water soluble. So it would be C. The oxidation product of that compound. So if we redraw it, everything stays the same. 1, 2, 3, 4, 5. And what happens is the hydroxyl group, I don't know if I just draw everything else on as normal here, the hydroxyl group becomes a carbonyl group. So then if we to name this molecule, there's a long chain of 1, 2, 3, 4, 5. The carbonyl group's on carbon 2. Because it's in the middle of the chain, it makes it a ketone. And then 1, 2, 3, 4 is the number of the branch carbon. So it'd be 4-methyl pentan. Oops. 2-on. So this one's on the practical applications or aspects of titrations. So to properly fill a burette, you would rinse the burette through with whatever you're going to put in it, the standard solution, which in this case is probably will be the acid. You would then fill to above the 0 line with the acid, drain some of it, and then take the reading from the bottom of the meniscus. So we're not rinsing with water, we're rinsing with the acid, but we're reading from the bottom of the meniscus, not the top. The most suitable solvent, so you're wanting the one that is most similar in structure. These two molecules here are hydrocarbons, so we want the solvent that is a hydrocarbon, which would be pentane B. Concentration is 0.06 moles per litre. What is the reaction time? So if we read off the graph, 0.06 moles per litre, the rate was 0.004. So all we do to work out the time is do 1 over the rate. And if you put that into your calculator, didn't really have mine at the ready, you get 250 seconds. And the time's always in seconds because the relative rate is per second. So butane reacts with oxygen as shown. 100 centimetres cubed of butene was reacted with the excess oxygen. So I'm going to put 100 centimetres cubed above the butene because it told me how much of it I have. Compared with the total volume of gases before the reaction, what would be the total volume of gases after complete reaction? So we need to work out what volume of gas we would actually produce. So the things that are gases on the product side are these two things. So if we're reacting 100 centimetres cubed of butene, then that means we're going to make 400 centimetres cubed of this because it's 4 moles, and 400 centimetres cubed of this because that's also 4 moles. To react all the butene, we're going to need 600 centimetres cubed of oxygen. So our total volume of gas we're going to use up on the reactant side is 700 centimetres cubed. The total amount we're going to produce is 800 centimetres cubed. So the difference between them is 100. We're going to end up with 100 centimetres cubed more of gas. Which of the following solutions, when added to the equilibrium mixture, would favour the forward reaction? So for these, I always recommend writing down the ions that you're adding. So sodium chloride, Na positive, Cl minus, H plus and Cl minus, Na plus and OH minus. And then when you get one that looks a bit weird, just look in the equation for it so you can see it's here. So CH3, COO minus, and then Na plus. So sodium's not in the reaction, and it's one of these ions that doesn't really interfere with anything, so it's not going to do anything to our equilibrium position. The chloride ions, they're not in it either, and they're not going to form any precipitates with anything, so that's not going to have an effect. B, hydrogen ions. If we add more hydrogen ions, it's going to shift to remove them, so that's going to shift it to the left, so actually favouring the reverse reaction. Again, the chloride ions aren't in it, so they're not really going to actually do anything. Then sodium ions, again, not in it, not going to do anything. Hydroxide ions, so they're not in it, but you need to remember that hydroxide ions remove hydrogen ions. So if they remove the hydrogen ions, it's going to shift the equilibrium to the right to remake them. So that's the one that's going to favour the forward reaction. Just to double check, D, the sodium's not going to interfere. If we add more of the ethanoate ion, then what happens is the equilibrium is going to shift to remove it. So that will actually shift left as well and favour the reverse reaction. Which of the following correctly shows the potential energy diagram for the above conditions? So the enthalpy of the reactants is 30, which means we want it starting at 30. All of them start at 30, so that doesn't help us rule any of them out. The activation energy of the forward reaction is 110, so that's like you have to put £110 into your bank account. So it has to be 110 up from 30. So that means it rules out A, because that's only going up by 50. And B is only going up by 80. This is my mental maths. C is going up by also 80. And D is going up by 110. So D is our correct answer. For the activation energy of the reverse reaction, that's 70. So it means the products need to be 70 underneath 140, which is here at 70. They're not high enough in these ones. Or that one, it's right, it's at 70, but the activation energy is not high enough. According to Hess's law, the AH value for Z to Y, so for these, imagine Z to Y is the road you're trying to take, but it's closed for the day. So to get from Z to Y, you have to go the other direction and take different roads. So we're going to go along this road, but we're going the wrong way up a one-way street because the arrow's pointing that way. So we have to change that to plus 210. We're going in the correct direction on this road, so that stays as minus 50. And then we're going along the right way on this road as well. so that stays as minus 86. So then if you add them all together, or take away as the case may be for some of them, then that gives us positive 74, so be B. 50 centimetres cubed of a 0.1 mole per litre ammonia solution was transferred to 250 centimetre cubed volumetric flask. The final concentration is, so we're trying to work out a C, so C question mark. We're given a volume of 50 centimetres cubed, and we're given another concentration, which is 0.1 moles per litre. And we're putting it into a solution that is 250 centimetres cubed. So to work out the final concentration, we're going to need to work out the moles of ammonia that we've put in. So don't forget to change your volume into litres. So divide it by 1,000. So N is always C times V, so that would be 0.1 times 0.05. So that means we've added in 0.1 times 0.05, 0.005 moles of ammonia. So if we've got 0.05 moles of ammonia in our new solution, the concentration of that will be N over V. Again, put your volume into litres. So 0.05 over 0.25, which is 0.2 moles per litre, which would be 2.0 times 10 to the minus 2. They've just put it in scientific notation to be horrible and confuse you. So an experiment involves reacting 0.02 moles of silver ions with ions of a group 7 element to form 2.868 grams of precipitate. Which of the following is the precipitate? So we've been given a number of moles, so I'll write that down here. And we've also been given a mass, which I will write down here. So what we can do is work out the GFM of this thing. So the GFM, which we don't really ever use the mole relationship really to work this out often, but if you have the triangle, the GFM is equal to M over N. So 2.868 over 0.02. So that means the GFM of the thing we're looking for is 143.4. So because all of the compounds have silver in them, we can go and look at to see what the mass of silver is. Oh, gone too far. So why can't I find it? Here it is, sorry. So silver is 107.9 grams. So if we take that off the GFM we're looking for, it just means we can then scan through to see the mass of the substance. So we don't have to work out all of the GFMs. It might save us a little bit of time. So that should give us 35.5, which is chlorine. So it would be silver chloride. So last one, a titration experiment was carried out to determine the concentration of vitamin C in orange juice. A sample of orange juice solution was pipetted into a flask and 10 centimetres cubed water was added to dilute the sample. Starch indicator was added to the flask. The mixture was then titrated in the flask using iodine solution of known concentration. Which line in the table shows the most appropriate apparatus to use when carrying out this procedure? So the type of flask you always use for titration is a conical flask, so that rules out C and D. And for adding the water, you ideally would use a pipette, but they've not given that as an option. So the next best thing after a burette, which they've not given as an option, it would be the measuring cylinder, so A. But my advice would be anytime they ask you about measuring the volume of a liquid, it's always a pipette of that exact volume, or if you don't have a pipette of that exact volume, then it's a burette. So I hope that helped, and if it did, please give it a like. Don't forget to subscribe, and I'll see you again soon.